So delta of n, when you see this bracket, the square bracket, implicitly we are doing discrete time and n is an integer. This guy is the Greek symbol for delta. And when you see the delta function, it is used in two cases, the continuous time and the discrete time. And we get delta of n. So immediately we draw n, and we know it's a function, and this is y of n equals to delta of n, and we're interested in this particular function. Delta of n is nothing but a function that at n equals to 0, he has a value 1, and at every other values of n, he has a value 0. So this is a very simple monster. Yeah. So if you look at the right hand side showing the slides, this is a definition. Delta of n is equals to 0 for all n not equals to 0, equals to 1 for n equals to 0. So it's nothing but a spike going up to height 1. Now, if you draw this guy, he is belonging to real because he's time. This guy is no more called Kronecker delta, which is the one on top. He is the direct delta. They are cousins. One is in discrete time, one is in continuous time, and his definition is a little bit different. X-axis is time, y-axis is the function with respect to time, and if we write this, then what we are trying to get is a function that looks like this and has nothing else. He is a spike, he's an arrow going to infinity. So look at that figure over there. He's an arrow going to infinity, only at time 0. He has no width. Yeah, only at time 0 he goes all the way to the top, to infinity. So he doesn't have a value. What value he has is using the integral. If we integrate from minus infinity to infinity, in fact we don't even need to integrate from minus infinity to infinity. There's nothing to integrate between here. So we are only integrating this little small part, which is sitting near 0. And when we are integrating that little part for this function, that guy goes to infinity, then we say that the area under this function is 1. That's it. That's the direct delta. And in continuous time, we use it all the time. All right. Now, so why do we bother with deltas? They must be interesting, right? Because if they are not so interesting, why do we want to do it? If I give you a sequence like this, and pictorially, I'm going to draw it for you now. So we have a sequence that looks like this. What I'm saying is that we can decompose it into deltas because xn is equals to this guy plus, if this value is a, this value is b, this value is a, this value is b, plus nothing else. Agree? So this is the first use, and it's a very important use. Then you say, what is the point? Why do I want to break a function that looks like this into small little parts that looks like this? First, let's talk about the definition. This is the scaling part. Second, this is also a delta. This is a scale delta, delta n minus 1. He is a delta function scaled by b, delayed by 1. So far okay? So now you see that I've broken a complicated function that have two spikes going up with amplitude of A and B into these guys, A delta n. So now I can write xn equals to A delta n plus B delta n minus 1. Okay? Now this is very powerful and important concept. It looks trivial, but when the system is linear, linear system, then something very exciting happens if we can break the signal down. What is it? The output can be studied with respect to the individual input. This guy can be studied only with respect to this guy. This guy can be studied with respect to this guy. And because the system is linear, the sum of the individual response is the sum of the input response for this input. Let me repeat that. You understand the word linear system? Linear system means I can break my input into small parts. I send it, the small parts. Okay, let's try. X1. I have Y1, for example. Can? Let's say alpha X1. I have alpha Y1. Can? Where alpha is a real. This is a linear system. Second one. The same linear system. I have X2, and you guys say this is Y2. If I have beta, then this guy is beta Y2. So far, okay? So alpha times X1 is scaling. I am scaling my input. Alright? Now what else? Linear means alpha X1 plus beta X2. What's the answer? The same linear guy? Yes, alpha Y1 plus beta Y2. So the idea of a linear system means I can break my input into small little parts, study the output, and sum it up. That's all. So if the system is not linear, this equation doesn't apply. This is called a superposition. Okay, doesn't apply, and then we can study a thing. So this aspect, scaling. Okay, this aspect, the additive property of the linear system. Scaling and additive property makes up a linear system. Why are we interested in that? Well, we're interested in that because if we can decompose the signal into sum of scaled and delayed deltas, then we can derive the convolution equation, which you guys should know, right? You have done the convolution equation. Then if you doesn't understand the convolution in the past, if you apply this principle now, you will be able to derive it. What else? What other things we are interested? Why are we interested in deltas? We're interested in deltas because of this. Okay, you got this figure. Let's try have a delta. We like delta because we can do this. This is the system H, and this is our input equals to delta of n, which is nothing but and nothing else in time. So my input is delta n, means I am sending 1 at time index n equals to 0 and nothing else. I send it to my system, and my system will output something. For example, it will output this. Okay, just for example, and nothing else. If I send an input to a system and it generates something and I observe it, this something is called the impulse response because the input is called impulse. Therefore, the system output is called the impulse response. So now you understand in previous courses, whenever they talk about impulse response, it's nothing but I send an impulse to a system, I observe the output, it's called impulse response. Right? So now you understand the first two lines. This impulse. We can generate an impulse response using the delta n. Last one, which is a bit more difficult to understand, is we'll just briefly say delta n, if you perform a Fourier transform on it, you will see that it composes of energy, equal energy at all frequencies. It is a signal that contains all frequency with the same amplitude, 1, for example, or the same energy. Using that, we can study the frequency response of a LTI system. So you see the three important uses of the delta.